Welcome to Bitcoin Fixes This, where we explore the impact that Bitcoin will have in all aspects of society. Today's guest is Giacomo Zucco, physicist, programmer, and Bitcoiner. We talk about his interest in physics, what's happened to the progress in physics, and the connection with math. Giacomo also tells us about how metaphysics and the desire for determinism to be true affects the study of physics itself. Giacomo is a deep thinker and accomplished Bitcoiner. I've been privileged to know him through the Bitcoin space and know that he's had a lot of different thoughts on different issues. We talked about physics because as noble as the science seems, there's an undercurrent of decline that's largely hidden through discussions of largely unprovable things like string theory. I hope you enjoy this episode. Giacomo, how's everything going, man?
Fine. Looking forward to travel again. Next destination, Mexico, with you as well, I think, right?
Yeah, I'm going to be there. But yeah, like, how's everything been for the last year and a half over in Italy and Switzerland?
Yeah, complex. At the beginning, very bad in Italy and very good in Switzerland. For the first wave of this madness, Switzerland was mostly spared. And then it basically shifted. In Switzerland now, we have there was like this referendum to cancel this COVID restriction, and the referendum was lost. And there was another emergency law about terrorism, which is basically Patriot Act on steroid. So now everybody can be spied upon in Switzerland as well. So it's quite bad, the political climate. That said, Bitcoin nerds had a little bit less to suffer than normal people because we were already kind of computer oriented, except for conferences and travels. The very sad thing was to miss Bitcoin Miami conference. That has been a bummer.
Yeah, that must have been a bummer. And, you do travel quite a bit for this stuff. And it sounds like you didn't get to, but at least you got to spend time with family, no?
Yeah, that's true, actually. And also the time with family was not really ruined by the situation because the kid is 3 years old. So she was not really disrupted in her life or anything. She was too young to notice craziness.
Okay. Well, so I brought you on the show because I know you have like a background in physics and everything. And it's, I was a math major, so I like math, and physics was one of those things that I was good at, not really that passionate about, but I did have quite a lot of interest in it. So I want you to tell our audience sort of what your academic background is and what you did and with physics and how you got into it and all that.
Sure. So the first thing to know is that before Bitcoin, I was having problems with being constant, and I had a problem of discontinuity of interest. So all my life, I wanted to be like a singer or like a politician or many other things. When I was choosing my high school, I wanted to be an archaeologist, but I have like a very distorted vision of what an archaeology does. My idea was basically Indiana Jones, so fighting Nazis in the jungle. So I studied like classical studies with history and anthropology and stuff like that. And then after high school, I was so bored with all the humanities, then I wanted to do something hard science. At the beginning, I was interested in genetic engineering. So I started to study that like in the last year of high school. And I've been told that the best way to pursue it was to study medicine and to become a medical doctor and then to do genetic studies. But that seemed a little bit long. So something very funny happened. I know you will probably not believe it, but we tossed a coin. There was a friend of mine. I decided between physics and medicine, and I was undecided too because physics was also getting pretty interesting. So we just tossed a coin, and he ended up being an anesthesiologist, and I ended up being having a degree in physics. So it was at the end, between medicine and that, it was the toss of a coin, literally.
Okay, so you decide on physics through the toss of a coin, which I'm sure like that must be like the craziest story. You decided your fate for like the next 6 years on the toss of a coin, but you went to university presumably, and what happened?
I did. First of all, toss of a coin is a very interesting physics situation. There is a lot of questions about probability connected to that, so it's not that disconnected. So I registered, and I was not an excellent student, I would say. It was the main Milan University. I was pretty good at. So one of my problem was the complete lack of mathematical background. I had in high school in Italy, classical studies. They say it's very good for the mind, for the general culture and for the general reasoning. But indeed, I did not know anything about calculus. So like I couldn't do any integral or derivative, zero, completely zero, my first day in university. And I couldn't do any linear algebra. So I didn't know what the matrix was. So as you can imagine, I was pretty good. Like I had like maximum votes on history of physics and humanistic bullshit like that. But on hard stuff, I really had to learn everything from scratch. But in a way, this basically helped me to be very. I mean, people who were already very good at math, they didn't need mental shortcuts. They didn't need to get the physical picture necessarily very, very strong because they were good at math. So they could just calculate. I was very, very, very bad at math. So I had to basically become better at understanding, at trying to unify, and I became better at reductionism, I would say. I started to write equation cross different fields in order to understand how to connect the stuff I was studying. And I became, I think, better at idea consistency probably than some of my colleagues, while remaining very, very bad at math. But then Wolfram Alpha with Wolfram Integrator came into my life, solving all the math problem automatically. So my handicap was completely nullified by Mr. Stephen Wolfram.
So you continued studying. What branch of physics did you then go into?
It was theoretical. My final dissertation was theoretical physics, and it was about hypercomplex numbers, especially Hamilton's quaternions, but also Clifford algebra, more general, applied to special and general relativity. So the idea, just for the audience that may not be super into this stuff, I guess many of the people listening know what complex numbers are. Basically, you extend the numbers in order to have a square root of -1. And many engineers and mathematicians discovered that when you have this kind of numbers, you can easily represent two-dimensional stuff. So you can represent rotation in 2D, you can represent the plane and stuff like that. So Mr. Hamilton, not the same of the musical, not the founding father, not the central bank communist, but the other one, the Irish mathematician, he basically tried to extend these numbers in order to do something which is even more than complex, which is hyper complex, in order to manage 3 dimensions, to have 3D calculations. He succeeded, but he ended up with a 4-dimensional stuff with a strange signature, like with a time that was squaring to negative, and actually space was squaring to negative and time to positive. So it was weird. Nobody knew what to do with that. And so it was let's say, mutilated into the vector calculus that we know today by Gibbs and Heaviside. And then people started to do just vectors. But when relativity came around, people had to extend vectors to quadrivectors or tetravectors, 4-dimensional vectors, in order to do relativity stuff, in order to do space-time Minkowski stuff. So what I discovered, but not like my discovery, what I found out in all books was that this kind of stuff was very good to manage relativity with a better, let's say, it's equivalent on the point of view of physics, but it's way better from a pedagogical point of view and from a aesthetical point of view, I would say. Every calculation is smoother, every calculation is nicer, even simpler. What people are also using quaternions inside computer science 3D simulations so that they work. And it was very interesting for me to do this kind of scientific archaeology, to take something discovered but then forgotten, and then coming back to be useful again.
Well, so just to sort of update our audience, like quaternions are kind of like complex numbers, but instead of just I, you have I, J, and K. I squared is -1, J squared is -1, K squared is -1. And you get weird things like IJ equals K and like JK equals -I or something like that. I can't quite remember which rotation.
It's all correct. It's all correct. And IJK is -1, and they are anti-commutative especially. So IJ is minus JI.
Right, right. And yeah, little known fact, I was in an a cappella group my senior year of college when I was studying abroad in Budapest, and we called ourselves the Quaternions because there was four of us. But but that I didn't realize that Quaternions actually had a physics sort of like component to it. I certainly knew that about complex numbers with like two dimensions and radial geometry and things like that. But can you describe for me a little bit more about how it sort of goes into relativity or how it relates? Because with relativity, you do have that fourth dimension in time, but it usually tends to be negative. So you have to do weird things with it. How do you fit sort of like quaternions into this model?
So the simple way to go to understand the connection, but it's not yet very useful, would be just to square a quaternion. If you square a quaternion, you see that you have the square of the real component. Instead of plus, you have minus the square of the second component, minus the square of the third, and minus the square of the last one. So basically, if you assign real access to time and the three imaginary quaternion access to space, you have this kind of metric which is t square minus x square minus y square minus z square. So this is the other convention than the one usually, but it's the same in relativity. The important thing is that you when you want to understand the invariant metric, the invariant, let's say, space-time distance, you want the difference between time and the rest. It doesn't matter if you have negative in time or in space. So this is the main thing, but it didn't quite work immediately, because if you square, you get a real part of the square, which is exactly the relativistic metric. But then you also get a vectorial part, which we cannot use in special relativity, especially. So people started to use complexified quaternions. So quaternions defined on top of complex number instead of reals, with another I, which is commuting with the other ijk. And now you get basically all relativity for free. You get even very complex phenomena. So basically, you assign the real component to time, and then you assign the I, let's call the other commuting negative square root of square root of -1. Let's call it, I don't know, L. So you get Ly as x, Lj as y, and Lz as basically, Lk as z. So you go with real and with complexified vector part. In this way, you get like Thomas precession, you get Lorentz rotation in a very, very nice way without metrics. You can get away with all the matrices. And this is especially nice when you switch to general relativity, because you can do something in a way which is nicer than all the matrix tensor and all this kind of ugly notation with tensor and Einstein notation with sum over index and stuff like that.
Yeah, which for me, like, that was sort of like the limit of my like tolerance for learning physics, was when you got to some of this notation that's just really ugly and difficult. It sounds like what you got here is when you use quaternions, which are actually a lot more elegant and easier to use, you get something that is a lot easier to sort of express some of these physics principles in. Is that right?
It is. It's simpler. You also have less degrees of freedom. When you define a matrix for rotation, you have redundancy in the degrees of freedom you have to write into the matrix. So you have to write like one number and then negative that number in another square of the matrix. When you use quaternions, you only use and complexified quaternions, you only use the degrees of freedom you need. And another very cool thing is not just that it's nicer to look at as a notation, but it's also less arbitrary, because why 4 vectors and not 5 vectors? Why 3-dimensional space and 1 of time and not 2 of time and 3 of space or 4 of space? With quaternions, you have mathematics itself creating this 3+1 symmetry, which is typical of space-time phenomena. So it's very, of course, you can just impose it, you can just define it ad hoc with the matrix, as you do in relativity. But with quaternion, it just emerges from fundamental mathematical choices. And that's not even the end, because if you try to go even more, so basically complexified quaternion units, they are the same as Pauli matrices in a Dirac equation. And if you take two complexified quaternion spaces. So if you go to something which is known as Clifford algebra 6, so with 6 square root of 1, so you basically get the Dirac equation for free. It's you don't have to discover the Dirac equation from physics as Paul Dirac had to do. You just see it emerge from pure math. Of course, it would be cheating to say that there is no degree of arbitrarity like there is. Why are you choosing exactly that Clifford algebra? But it's very nice to see that if you choose this kind of consistent and elegant mathematical number system, much of modern physics can be derived from math directly instead of discovered empirically. Of course, not all of it. Like with this kind of Clifford algebra, you can do the Dirac equation. You get some hint into the standard model of particles, but you don't get stuff like mass of the particles. So a lot of information is still completely missing, and still you have to put into the theory ad hoc. But it's nice. I remember that it was not a dissertation I gave just to get a degree. It was something I was really super enthusiastic about.
Yeah, and what it sounds like, correct me if I'm wrong, it sounds like there was sort of like this mathematical construct. You got quaternions, and I guess you have to complexify it by using, one other dimension of I or something like that. But naturally from that mathematics, you can derive a lot of the physics, which is very interesting to me. Like, because in a sense, the mathematics is very much metaphysical, and physics, of course, is physical. And you're able to derive a lot of the physical properties. They almost have to sort of emerge from this mathematical description, which seems to be accurate. Am I getting it right, or something to that?
You're absolutely getting it right. There is some kind of resistance to this notion because some physicists say, okay, but you're still choosing ad hoc stuff. You just know what the result must be. So you are cheating. You are basically searching across infinite mathematical structure, the ones that will recreate, for example, the standard model of quantum physics or general relativity, which I think is a little bit unfair. There is some of that. There is some level of, I know the result, I have to get there, and so I will make my choice accordingly. But really, like complexified quaternions, which are also known as the algebra of physical space. So if you want to Google around or DuckDuckGo around algebra of physical space, you will get complexified quaternions. And that was discovered by Hamilton again in the 19th century, before anything of this was useful or needed. So it's unfair to say that it was just created ad hoc in order to match physics. It was actually a line of research on pure numbers going on itself, and it happened to be very relevant for physics. And the nice thing is that this was abandoned, and all the results that modern physics achieved during the beginning of the 20th century, like the Dirac equation, people that didn't know about complexified quaternion, they had to reinvent stuff from scratch, like Pauli matrices or gamma matrices of Dirac and stuff like that.
So this reality sort of emerges almost, and it correctly made a lot of predictions, and these things sort of had to be rediscovered. In a sense, that's sort of like the essence of science, or figuring out sort of like the rules by which everything works. And it does seem like there are rules of mathematics which seem to rule over what's possible in physics and what sort of has to be. There's sort of like, like you were describing degrees of freedom. There's no degree of freedom there. It sort of has to be this way because of the way the math works. Is that close to what you were describing?
It is. There is some arbitrarity, but it's very, very limited. Even if you're honest and you go with logical natural choices, you end up with something which could have allowed Hamilton, if he didn't kill himself with alcohol, to basically, I mean, he was a great guy, but he was Irish and he died younger. But he could have probably discovered some of the physical feature of modern physics without any kind of photon spin experiment or double Fenditur experiment, double slit experiment or something like that. So yeah, I think this is a very good description. Of course, you are saying that this is typical of science, but we have to add that this is old school science, because new typical science is just ask to the government appointed scientist what is true and believe him without verifying. That's science now. This is another kind of science, very, very obsolete, I guess.
Well, tell us how you really feel about modern science. I just kidding. Well, so that brings us sort of modern physics, and especially like string theory and things like that, which I honestly, like, physics doesn't seem to have progressed all that much, since, I guess, quantum mechanics and things of that nature. I mean, like, you get like maybe better numbers, right? You have the Hubble telescope, so you can figure out like how far the redshift is and maybe get more accurate readings on stuff. But I mean, like, from my reading of physics the last 20 years, it just seems like academic masturbation. Am I wrong?
I think you are not wrong. I think that the only thing that saves physics a bit is that everything else is even more academic masturbation. Like if you go to psychology or psychiatry, that's literally nothing is reproducible anyhow. There is a complete reproducibility crisis, so nothing can be checked. It's all completely irrelevant. While in physics there is some degree of connection to reality, I would say that fundamental physics is really at a dead end. Nothing like the fundamental problems that the fathers of quantum physics considered indeed fundamental to solve, like renormalization in quantum field theory, in quantum electrodynamics. This is a very stupid thing. It's like you make the calculation, you get infinities, but then you find other infinities and you subtract, and magically you have the number that you want. It's just a trick. And Feynman knew that it was a trick, and everybody else knew it was just a trick. And they were like, okay, eventually we will discover the real fundamental reasons we can do this. And the applied science around the physics progressed in a good way, because we had transistors, we had new materials. The physics of materials comes from quantum physics. So this kind of provisional fundamental theories, they managed to give us a lot of applied engineering. But then the fundamental field itself didn't progress at all, and basically split into this kind of it's part untestable. Like string theory is literally disconnected from any kind of prevision and testability. And now you can read articles of string theorists just saying that, yeah, but this Popper rule that you have to make prediction, it seems like too strict. Come on, let's discuss other stuff. They are trying to change the norm of prediction and falsifiability, because it's completely M theory is completely unfalsifiable. You have an infinite number of degrees of freedom that you just adjust in order to get all the results that you want. And even if you think about the measurements of the early quantum electrodynamics, there have been some scandals that people that fixed the numbers, basically. People getting the number they were expecting because they were expecting it. And I think that the reason is not super sad as it would be otherwise. It's just that all the rest of the scientific enterprises is so much worse than physics that you give it a pass, basically. But it's bad. Also, the fundamental thing is that you have two fundamental theories. One is quantum mechanics that is consistent when you go non-relativistic, and it becomes almost consistent with a few tricks when you go relativistic with quantum field theories, but not really consistent because you have this renormalization. And then you have general relativity, which also has you have general relativity, the best theory at all predictions. Then it will predict a mass in the universe, but then the one you measure with other kind of indirect measures is more, and then you make up dark matter. And then it predicts this kind of acceleration constant in faraway galaxies, but then it's wrong. And so just that you have to add dark energy and a cosmological constant. So it's it's perfect in prediction because you are going to fix the prediction as you go. And these two theories, which are not very consistent on themselves, they are completely incompatible when you try to match them together. You get infinities all around everywhere. So right now, the cool thing will be to find something consistent. I think string theory is not only unfalsifiable, but is also intellectually, philosophically I don't know if some string theorist is listening to us and he will hate me, but I think it's ugly. I mean, ontologically speaking, you have to basically assume not only space, you don't get emergent space-time in an elegant way. You have to assume space-time with 12 or 11 or whatever dimension. You have from an ontological perspective, you have a very super heavy ontology with a lot of stuff you have to assume. And then you can have a theory that you can adjust with infinite degrees of freedom in order to match experiments. On the other hand, I think there are some interesting things for quantum gravity, like causal set theory and stuff like that. They are nice because they assume very light ontologies, like you only think about causal connections. And from that, you build space-time with three dimension and stuff like that. So everything emerges from from very small assumption. The problem is that from this theory, another example would be outside academics, would be the infamous Wolfram model. So Wolfram is starting from again the same Wolfram that saved my ass in university with the integrator, is trying to make the modern physics emerge from these basically rewriting systems, basic rules for a writing system, creating physics from scratch. The problem with these approaches is that they are more elegant than string theories. They are more minimalistic in ontological assumption. They are less arbitrary, but still they are very far from being easy to connect with the phenomenology. So, I mean, it's very hard to go from Wolfram to a measurement. And so, yeah, I would generally agree with the assessment of a very bad state of the current fundamental physics research.
Yeah, I mean, to me, like, when I do read popular things on physics, it's almost always about dark energy, dark matter, string theory, all of which seem kind of like fudges, right? Like you make up dark matter and dark energy because the equations don't balance. And it's like, okay, I guess the equation's fine. It's, it's a universe that's wrong, something like that. That's what it looks like to me as a mathematician or as somebody that's just sort of like looking at things rationally. It's like, okay, you have to add this cosmological constant to, explain something. It's like you add in all these fudge factors, or I guess what you would call, you add degrees of freedom for yourself so you can, explain the measurements that you're getting. It just doesn't seem like science anymore. You're just sort of making up crap in order to justify what you already believe.
Yeah, if I try to play the devil's advocate, I will say that when you are creating like new theories, you must be guided by empirical stuff you want to predict. Otherwise, it's not science. In this specific case, even I think the effort is not really consistent, and there is not. I think there are, well, we can discuss that, but I think there are some problems with the fundamental metaphysical assumption of modern theorists. If you read the fathers of quantum theory, like if you read, Max Planck, and you read about his ontological views and his metaphysical views, he was basically a non-realist and non-materialist and non-physicalist. He was thinking about like the human observer as something more important than particles. So he was taking this very strange metaphysical path. And I think that fundamental research was basically leading there in a way. And this was clashing with the typical modern metaphysics assumption. This was actually very consistent with the typical metaphysical assumption of a scientist, of a physicist of the 16th or 17th or 18th century. But it was at complete odds with modern materialistic and, I don't want to use the word spiritual, but...
well, I mean, they're denying sort of like a metaphysical reality. They only think, there's this world and that's it. It's a very materialist view, right?
Which is a very strong and heavy metaphysical assumption. So this is not being metaphysics free. This is having a very strong metaphysics assumption, which seemed to be very, very strong when Laplace was promoting this view in the 19th century, because with classical mechanics, this metaphysics of materialism, matter is all there is, was actually doing very well with classical mechanics. It was very consistent with this. But with quantum mechanics, I'm sorry, but it just doesn't. You can try to, you can still have a physicalist or materialist framework in quantum mechanics, but you need a lot of ad hoc stuff, like you need many words, and then with many words you don't know exactly how to do Born rule, but then you can do like Born physical wave, pilot wave, moving the particle, but then you cannot make it relativistic. So to be materialistic, or you need like spontaneous collapse of the wave function, but that's just not physics that has been discovered yet. So this is just an assumption you need only to protect your materialist metaphysics. So scientists today, they need to keep a 19th century metaphysics in spite of a science which is pushing the other way. And I think this is felt, and this is one of the many, together with the problems with academia itself, academic mechanism itself. I think this is maybe one of the elements. I think that this is a long discussion, so stop me if I get boring. But I think that quantum mechanics, it has been called counterintuitive or like confusing, but I think it is not. What it is very intuitive if you start from the typical metaphysical assumption of somebody that haven't studied science at all. Like a child or a caveman, and it becomes only counterintuitive to a typical Newtonian physicist that made a lot of effort in order to grow to grow out of this kind of assumption. So I make you 3 examples. The first example is discrete versus continuous. So when you are a child, I guess that it doesn't make sense. You get very impressed by Zeno paradoxes, like how can I throw an arrow if the arrow has to go halfway first, but before it has to go halfway, and so on. So these paradoxes usually make you think, this cannot be. At hand, space must be not infinitely divisible. At least this was my concern when I was a kid. Then with a lot of effort, people convinced me that, okay, but if you take infinite steps, but these infinite steps take infinitesimal time, so you multiply infinitesimal for infinite in this integral, and you get a finite time for the arrow to reach you. So you make an effort, a counterintuitive effort, to move from discrete and finite to infinite and continuous. But then when you get to quantum physics, you have to throw it away. And especially when you go to quantum gravity, you probably have to go back to assume that a Planck length, even if you don't go to quantum gravity, Planck length is something you cannot go under any kind of modern physics assumption. So you have to admit that you have to go discrete again. And then the second would be probability versus determinism. So when you are a naive external observer of the world, you know that everything is probabilistic. You know that you cannot really predict the weather tomorrow, that everything is out of your control. You can maybe predict like solar eclipses, which is the only thing. Basically, the reason ancient populations were looking at stars was that it was the only predictable thing. Everything else was extremely chaotic and unpredictable. Then with Newtonian physics, you thought you have to convince yourself that there is no chance, no real randomicity. Everything is deterministic, like a perfect machine, and it only appears to be deterministic in the macroscopic world because of ignorance. But then you go to quantum physics, and you have to admit that the universe is intrinsically indeterministic. And then the last, which is the more powerful, is you at the beginning, when you are a child, you cover your face, your eyes, and you think that the world disappears when you cover your eyes, because you know that you as an observer you give yourself a privileged point of view. Then when you learn physics, you have to painfully learn to throw yourself out of the equation as the observer, to ignore human observers as something interesting. You have to cancel free will, consciousness as just illusions and epiphenomenons, and you have to cancel all this stuff. And then you get to quantum mechanics, and you get to the interpretation of Copenhagen, and especially Wigner and von Neumann and Stepp. And then you get to hypothesis of consciousness for wave collapse like Penrose or John Eccles. And then you get to, a lot of interpretation of quantum physics or quantum Bayesianism, cubism, where the human observer is the fundamental thing, and the matter and energy are emergent things themselves. So human experience as the foundation, and matter as the emergent illusion and not the other way around. So this is pretty much, I know this blows a typical physicist mind, but I don't agree it's counterintuitive. This is just getting back to a more, I would say, even natural framework that was considered naive under the delusion of mechanicistic physics.
Yeah, and that's something that strikes me about your description is that sort of like the Newtonian mechanics and, pre-relativity, pre-quantum, all that stuff. It was very much about sort of controlling the world. And that's a control that a lot of physicists sort of have a lot of trouble sort of giving up, because when you recognize like what's actually going on in quantum mechanics, where it's a probabilistic model where you literally have no idea whether or not it'll go this way, that way, or it'll have this spin or that spin or something like that. That's deeply unsettling when you grow up with the assumption that everything in the world is knowable and that it's deterministic. In a sense, you get thrust back into sort of like a non-deterministic world, which is, I think, as you said, very much a part of the human experience. And that's what we experience every day. It's just that physics gives this sort of like false promise of, or at least Newtonian physics gives this false promise of, being able to control those uncertainties in a way that really it shouldn't.
Yeah. Laplace exactly said this. He said, if you give me all the positions and the momentums of all the particles, I can predict all the future and explain all the past. I don't need free will. I don't need God. I don't need anything as a new hypothesis. I just need positions and momentas. And this is all I need to predict completely all the future and all the past. Then the first thing that physicists had to give up was knowledge, because you had like a chaos science. You have basically nonlinear systems. So some things you cannot really know because small changes make a big difference. So it's impossible to practically know. But then with quantum physics, they had to give up the even theoretical. It's not even a point of knowing. It doesn't even exist. When you can have this experiment where you send a photon, and the photon can either go right or left, and then it gets gathered again, and then it goes either up or down. And if you look at one of the right or left choices, then the photon will only go up and it cannot go down anymore, just because you're looking, even if the photon is not passing through the way you are looking. So the fact that you are observing, this seems, at the beginning they tried, many physicists, they struggled, they tried to, Einstein himself, he was like super deterministic, even in a way, even more than
God
Newton.
Does not play dice is his quote.
Yeah,
right?
Exactly. And also he was using the term God, but he was a Spinozian. So his God was a materialist God and completely deterministic. And he believed in a block universe, like everything is already written. There is no choice. There is no real change. Everything already exists in 4 dimensions. So he had troubles with this and tried to falsify it. He tried to come up with this kind of thought experiments in order to find an inconsistency. And he ended up wrong in all these cases. Basically, quantum physics was right and Einstein was wrong. And it went even worse, because then you had like Bell inequalities and Allen aspect experiments about, for example, delayed choice. And now you have the delayed choice quantum eraser, where basically you measure something, and measuring, you will basically have the interference pattern disappear. But then you delete the information you have about that. And now that you deleted it before reading it, so you measure, you store the information, you delete the information, and now you have interference again because you deleted the information before watching it. So you really have, it's not that you are forced to come up with some kind of, let's say, consciousness-based ontology. But if you don't, you need a lot of effort about untestable stuff like parallel universe or pilot waves. You need a lot of assumptions.
You need additional degrees of freedom so you can fudge in and get whatever it is that you want, essentially.
Yet again. It's stuff that you cannot measure and you cannot predict. It's just stuff that you need only to save your materialistic metaphysical background.
And so that brings us back, I guess, to a more philosophical sort of argument there, which is that there does seem to be an agenda there, right? Like there is sort of like a materialist metaphysic that a lot of physicists want to be true. And in a way, they add these other things as a way to make that metaphysic true. It's almost like they want to be able to predict everything, or like had this sort of like 19th century view that you outlined earlier. Like if I know the position and velocity of every particle, I can know all of the past and all of the future. Like sort of this very like the world is already determined, and we are going to do what we're going to do. That seems to be an agenda here almost within physics that hasn't died despite all of the interesting observations that have been made, all the stuff from quantum mechanics and all that seems to contradict it.
Yeah, I'm not sure I would call it an agenda. I think it's an intellectual fashion. I think it's an intellectual trend. It can be as powerful as an agenda because peer pressure is strong, even if it's just for a fad, even if it's not an agenda. What I mean is that it's true that materialistic frameworks, materialistic philosophies, they can actually give power to some people, because if the world is predictable, then if I am in charge of prediction, I can just rule you. I can govern you because I'm the predictor, I'm the scientist. That's true, but the same goes with any other kind of metaphysical assumption. If we are in a theocracy and I'm the Ayatollah, I can still govern you around without any kind of materialistic assumption. So the point is not really that this interpretation is the only one that gives some kind of power. The point is that I think that the materialistic point of view just after Descartes, so already in the 17th century, it started to grow and fight the common sense. So the common sense was anti-materialistic. Everybody know that they have a consciousness. Everybody know that they have free will. Actually, everything we know, including physical experiments, we know those just because we have an internal perception of stuff. Otherwise, we could not even read.
Physics itself and physics rule, laws of nature, they're all metaphysical. It seems ridiculous to me that like strict materialism is even a thing, that it's not intellectually consistent at all.
And I think that to everybody, it seems ridiculous. Almost everybody. When the first, I would say, heroic, even if misguided, people started to promote this view, like Hobbes and a few others. But then these heretics, they started to basically, within the frame of Newtonian physics, this assumption seemed lighter than the other way around, because the success of Newtonian physics was very, very huge and completely impossible to stop, they seemed. So basically, you had this kind of shift. And with the shift of philosophy, you have a shift of power, because, of course, now you can overthrow the old school with the new school. And then what happened is that this kind of mechanicistic point of view started to spread outside physics into medicine and psychology and even history. If you think about Marxist, like Frankfurt historicism, where all the history is just possible to calculate with this kind of social forces. You just go down and calculate, and everything is deterministic, like historically inevitable, like in Marxism. So this basically started to flow out of science into out of physics into social science. Then at the heart of physics, where all this stuff started and where this stuff was coming from and invading every other field, there was the implosion of this assumption with quantum physics. And the first people accepting and creating, so the first people hinting at quantum physics, like Einstein, they never accepted this. But the first people really developing quantum physics, like Planck and Heisenberg, they literally adopted this kind of non-materialistic assumption. Then you have this kind of incomplete revolution, because I think that probably part of responsibility is also that this kind of quantum mind stuff also started to get used by Eastern spirituality types with very ambiguous hand-waving theories about, quantum. If you search on internet quantum something, you will have 99% bullshit, just like if you search for blockchain. You will have quantum healing and quantum something. Quantum is basically stuff to... Quantum is a new buzzword to sell you some kind of pill or some kind of investment scheme. So it's mostly scams. And I think that one of the reaction was to not take the fundamental challenges of quantum physics seriously. So most people I knew in university, even professor, they were like, how does the wave function collapses? And they were like, oh, this is just decoherence. But decoherence is not that. Decoherence doesn't solve anything. They were actually, what they were thinking was decoherence plus many word theory, which itself is completely non-testable,
and way too many degrees of freedom on the many worlds assumption.
Yeah,
That's like, I can make anything true.
Yeah. Of course, I mean, you can make it more consistent, but the point is that it's like,
it's like issuing tokens on an altcoin. You can make any business model work if you're issuing your own money. You can make any physics work if you're making a many worlds assumption.
And when I gave them mostly non-physics paper, but philosophy of physics paper, actually basically pointing down to the process of thought, explaining clearly that the coherence doesn't solve the tension between observer and unitary evolution in physics, they were surprised. Like they were, oh, but I've been told that there is just the coherence and it's solved. But it has not been solved. It is still the same. It is exactly the same kind of mystery that was for Heisenberg or von Neumann or Wigner. Again, the only difference, and even more for Bell, the only difference that people just stopped thinking about that and tried to hide this embarrassment for materialism under the rug. And they use a strawman argument. If you point to like Copenhagen interpretation or cubism, they will just say, oh, come on, don't go all quantum healing Buddhist priest on me. They will just strawman you into some kind of spiritualistic hand-waving guru type in order to avoid the hard questions.
Oh, so what are the hard questions? What is sort of like physics not courageous enough to actually face? Because it feels like it's been stuck for so long. And there, at least like the fundamental aspect, I'm sure there's like a lot of progress in material science, physics, and, fluid mechanics and things like that, which has been used by engineers for good. But like the fundamental stuff, there seems to be just sort of like this metaphysical mental block that physicists can't seem to get over. So what are the big questions that they're not facing, that they really should be answering, but aren't?
Basically, I think that in a very simple way to put it, missing some nuances, of course, but we can get into that later, will be that you have two choices with modern physics. Either you follow the natural, the most obvious Occam razor interpretation, and then you have to gradually accept that the fundamental pieces of reality are stuff like information, experience, choice, and not really electrons or stuff or energy. And you go in that direction, and basically you go in this kind of it from bit framework. But it from bit seems actually harmless because it seems just computer science. It seems like computer science is taking over physics. That's true, but it's even worse because it's computer science plus stuff like consciousness, personal human consciousness taking over the world. And this is more embarrassing if you go in that direction. The other way to go is to keep, to save, to protect your physicalist, materialist view and to overcomplicate things a lot in order to have this kind of 11 dimensions with strings and pilot waves and multiple words, and apparently to choose. And everybody recently in academia are moving to choose the latter and not the former. And I think this is, even from the past, this is not just a metaphysical block. This becomes a practical block because when your metaphysics is super complicated just to save your metaphysical assumption, when you have to create all these ad hoc hypotheses just to avoid facing the interpretation you don't like, what happens is that you lose, is that intuition becomes harder because you have to assume a more complicated model just to save your metaphysics. And more of that, you don't have heuristic help from from interpretation. So let me try to clarify this. If you interpret quantum mechanics with interpretation of Copenhagen and consciousness causes collapse and Step or Wigner, everything is fine. You will have a perfect prediction. If you interpreted it with many words plus Born rule, which you have to stack in a little bit ad hoc way, you can still do perfect prediction on the things you can see. Of course, most of the things you cannot even test, but at least the things that you're going to see, you can predict them. So it's equivalent from the point of view of experiments, but it's completely different from the point of view of heuristic. So what are you going to do to discover new stuff? For example, to go into quantum gravity. When you want to discover new stuff, when you want to expand your knowledge and not just to reproduce the current knowledge, you need the guide of a consistent view, of a consistent vision.
Of a theory, yeah.
Of a theory, yeah. And my guess is that overcomplicated theories that have the only purpose of saving materialism are not the best guide to discover new stuff.
And that seems to have held back physics for a while now. I mean, like the problems that so I've been studying cosmology lately, and like just, reading about like the inflation problem, like why it exists, why physicists have to do it. And it's like, it just seems so incredibly arbitrary, right? Like to add inflation to Big Bang in order to make sure that the temperatures are more or less even wherever we look. That's an observation that we have to fit into this theory. And the only way to do that is, like some very small fraction of a second after the universe was born, it somehow like, grew way faster than the speed of light, like really, really quickly to a point where, it had enough time to mix, but it didn't have, it just sort of had to expand. And it things like that are just all over physics, right? Like, we're talking about dark energy, dark matter.
Well, exactly. One thing I appreciate about inflation is that they toss in this other particle, the inflaton, but they don't call it dark inflaton, which surprised me because every time they don't know how to fix the theory, which is making wrong prediction, they make it dark something. So, okay. But, dark inflation.
It seems kind of dishonest because you're adding in all these fudge factors. It reminds me of the Fed, right? Like the CPI number always comes in at 2% because they manipulate it that way. Although, obviously this month they had to say it was like 5.4 or whatever.
Yeah.
But there's sort of like, it just doesn't seem honest anymore. And I think you've sort of identified where it comes from. It's sort of like this deterministic metaphysic that they want to have, and they add other stuff so they could keep that particular worldview instead of sort of letting the science show them what it's supposed to be. Instead, they craft sort of like these, elaborate theories. It reminds me of epicycles, right? Like where you can draw
perfect example.
Anything. Yeah.
Perfect example. The geocentric model can work as long as you add a lot of super complex motion. So the epicycle theory was basically covering all the empiric facts back then. It was not lacking, but it was absolutely overcomplicated just to preserve a point of view that was against the simplest interpretation. So you're absolutely right. Well, I think that we are giving a little bit of we're assuming noble intentions, because even if it's a wrong metaphysics and if it's dishonest metaphysic protection fed, still we're talking about philosophy. There may be another more gross and down-to-earth explanation together with this one about determinism and consciousness and free will, which may be the fact that with some physical theories, you can ask for government funds in order to build more accelerators and synchrotrons and cyclotrons. Without these theories, if you go into more consistent stuff, you may not have excuses to spend all that money building stuff. So it may also have some kind of more economical component to it.
So you're saying that because there's free money available, essentially through grants and so on, that research tends to go in a more expensive direction, which instead of the more truthful one.
Our friend Seyfedian would say fiat physics.
Yeah, wow. Well, so walk with me through sort of how physics changes as we go on more of a sound money Bitcoin standard, because clearly something is broken about the current academic system. And I think, anybody that's in the university system or anything like that knows, like it's not just physics, it's like everything. It's the incentives are off, and, it's publisher perish. It's writing papers that don't say anything, that aren't reproducible, that, that are sensationalistic in some ways. Things are very off, even in a hard science like physics. So how does Bitcoin change things going forward?
I think at least three effects. One effect will be just to to remove part of the distortion of free money newly printed in order to influence stuff. So we have this kind of elite that can extract borderline infinite money with the Cantillon tax, and they can use it to buy everything, which includes buying intellectuals, buying philosophers, buying scientists. Of course, I think that the priority, the typical shopping list of these people, they don't include physicists at the top of the list. They mostly include like medical doctors, as we can see right now, or economists, especially to justify what they do, or social scientists. So this is people in power. They want to buy scientists that tells them that they need to stay more in power. But I think we learned that even fundamental physics can be politicized at a very high degree. For example, there was like in China during the Cultural Revolution of Mao, there have been a physics professor killed because Western quantum mechanics was literally, it was an anti-Marxist philosophy. So this stuff has been actually, there has been other people thrown in jail in Russia and the Soviet Union because they were political interpretation of fundamental physics. So removing this kind of distortions may help removing this kind of removing economic distortion may remove a part of intellectual distortion. Another kind of effect could be more indirect, and it will be just the collapse of the authority principle that is the base of the modern average Joe epistemology. So average Joe today thinks that there is the expert. The expert is the one appointed by the government, and he knows what to say, and he's always right. Even when he contradicts himself in 2 minutes, he's still right. And you just have to trust and never to verify. I think that I brought up this discussion a few days ago in another conversation about nutrition. And there was a classical question, why are you Bitcoiners so much like talking about nutrition all the time? This doesn't have anything to do with money. Well, not much directly, maybe. There may be some direct connection, but indirectly, the point is that when you recognize that the top experts in monetary theory and economics are literally either morons or dishonest criminals or both, and those are all the highest authorities in this field in the world, then you may have a epistemological clue that maybe you need to verify not just your software, not just your keys, not just your monetary base, but even other stuff. So this kind of attitude, Bitcoin forces you to verify more and trust a little bit less, or at least trust within reason and with caution and with adversarial mindset. It's not that you cannot use authorities anymore, because there is division of labor even in knowledge, and you cannot know everything just re-deriving it by yourself. That's just practically impossible. You have to admit skills, experience, and specialization. You have to listen to experts. But the point is that you have to ask yourself first, is what expert, can I at least check logical consistency of what the experts are saying? Because if what they're saying is logically inconsistent, at least at that layer, I can already debunk it myself. Second, does this expert contradict any other expert? And is this like a political expert monopoly, or this is like a real free market of ideas? And then you have your second clue. And third, basically you have is there a strong reason, a strong incentive for this guy to tell me this? If somebody, let me give you an example. You have an old couple in a house, and then you have these guys knocking at the door, and they have a knife and very, very angry face. And they say, we have to enter to check your electrical system. And then the old couple will answer, I don't trust you, I don't let you in. And then they may say, are you electricians? You are not. You are not expert in this. You cannot know if my intentions are good, because you're not experts in the field of electrical systems. So you have to let us in. The point is that if there is a strong reason to think that somebody wants to control us or hurt us or take our stuff, then it's not a matter of division of competence anymore. It's not a matter of expertise. It's a matter of trust and adversarial thinking. So this is the second more indirect way. And the third one may be that, as anything else, some money can help. Some money can lower time preference and help investing in non-unstable, non-provisional, but sound and intergenerational endeavors. And fundamental physics is such an endeavor. There are two ways to do fundamental physics: either provisional hack just to keep it together, or effort to search for something stable and fundamental in order to do something in the future to build upon that. And I think that some money in general can incentivize this kind of behavior across different fields.
Mm. Well, this hour has just absolutely flown by, and I feel like we could probably go for another 2 hours, like discussing various things in physics. But I do want to respect your time and so on. So, where can people find you, and how can they go find your dissertation?
Yeah, dissertation. Well, it's not even online. I think I may publish it. So people can find me on Twitter and Giacomo Zucco, GIACOMOZUCCO. And if I get banned from Twitter, I have a Telegram channel with the same name, and also I have a website. Even if in the website I have to fix it because the videos, they are not working. I have to fix a little bit the website. But anyway, giacomozucco.com. You can go on the website. You can check some stuff. There is nothing about physics there. Also because so I told you at the beginning how it started, but how it ended was that while after my degree, a multinational hired me to do design of payment systems in Accenture. So I did that for 4 years, and then I discovered Bitcoin, and then I focused only on Bitcoin since 2013 until now. So I don't do physics anymore at the professional level. So I don't really publish anything at all. I just discuss with friends when I want to discuss. But there is nothing like about my dissertation on my website or anything. I still have the digital version of it, I think. So maybe I can just publish it somewhere.
Okay, awesome. Well, thanks for joining me. That was amazing. Yeah, thanks.
My pleasure. And also a different topic sometimes. It's fun.
Unchained Capital is a sponsor of this podcast. I've joined Unchained as an advisor on the engineering side, and I know the team well, and I know what they're building. It's very exciting. If you need multi-sig, collaborative custody, or a Bitcoin native financial services partner, learn more at unchained.com. Well, that wraps it up for this episode of Bitcoin Fixes This. Giacomo Zucco can be found at Giacomo Zucco on Twitter. Until next time, fiat delenda est.